Hello everyone, I am Murali Krishna Kancheti and I have my teammate Rohit Singamneni. We are here to discuss on our ML research project called MedGen, and it is an NLP toolkit for medical text processing. So before choosing a research project, we were quite researching on different aspects or different models in machine learning. Since we are quite interested to learn more on NLP models, and we chose MedGen because it has all the applications and all the use cases of NLP. So, okay, let's discuss on NLP. So, NLP stands for Natural Language Processing, which is a subfield of artificial intelligence. So, it focuses on the interaction between computers and human being. So, it focuses on the interaction between computers and humans using natural language. So, the main object of NLP is to enable computers to understand, interpret, and generate human language in a way that is both meaningful and valuable. So there are different applications of NLP that we can see in real world every day, and those applications include text processing and understanding, language translation. It is also known as machine translation, speech recognition, image extraction, question answering systems, creating chatbots, and text summarization, recommendation system, documentation analysis, and many more. So recent advances in deep learning, especially transformer-based models like GPT and BERT, have significantly improved the capabilities of NLP systems in recent years. So in this research paper, the publishers used different NLP models on different use cases. So we have read and understood each model for different use cases, and my teammate is going to tell more about the MedGen toolkit, and then I'll be taking over. Thank you.
Hello. Yeah, thank you, Muri, and I will get on with the MedGen right now. So let's get into it. So as Morley said, we choose MedGen because it uses a lot of NLP toolkits, and it is we used an extensive natural language toolkit specifically crafted through processing of medical text and designed with needs of biomedical researchers and healthcare professionals in mind. It offers an accessible, all-encompassing solutions that requires minimum programming expertise, and it has also features like generative functions, basic NLP function, and query and search capabilities. So again, in generative functions, there's 4 advanced generative functions, which is question answering, text summarization, text simplification, and machine translation. And in the NLP functions, it's seamlessly integrated with 12 fundamental NLP functions, covering tasks such as word tokenization and sentence segmentation. So we use MedGen because there's a lot of challenges in medical text. There's a lot of ambiguity, frequent abbreviations, negations, and segmentation complexities characterize medical text. Manual curation is time-consuming and labor-intensive. Then, by using NLP algorithms, we can form a transition from shallow embeddings to advanced architectures like BERT. There's a category. It's we use BioBERT, Clinical BERT, PubMed, and are the examples of domain-specific pre-trained language models. These models enhance NLP efficiency in biomedical and clinical domains. So we can increase the NLP task effectiveness by which includes text classification, named entity recognition, text segmentation, language translation, and text generation. Advanced models significantly improves the performance of this task. So despite advanced techniques effectiveness, there's a noticeable gap in practical utilization. Biomedical researchers and healthcare professionals face challenges due to technical intricacies. So for that very reason, we need a user-friendly toolkits. Its aim is to streamline complexity in medical text processing for individuals lacking computational or programming expertise. In this table, we can see that there's a lot of different toolkits out there for the medical in the field of medical, and MedGen provides all the functions by these. It also represents a comprehensive comparison with existing toolkits with uh, evaluated through human assessment, basic NLP functions encompassing abbreviations, extraction, sentence tokenization, word tokenization, and UMLS concept extraction, named entity recognition, document clustering, POS tagging, etc. All those. And multiple choice are considered it an important note that while not every toolkit incorporates all 12 basic NLP functions, MedGen distinguishes itself by including each of these functionalities. The table also offers an insightful overview, highlighting the distinctions and commonalities among various toolkits, with a specific emphasis on the inclusion of essential NLP functions, where MedGen stands out for its comprehensive coverage. The next topic is materials and methods. We conducted a meticulous fine-tuning process for 32 domain-specific language models, subjecting them to through evaluation across 24 established benchmarks. To ensure practical relevance, we engaged clinicals in manual reviews. Furthermore, we enhanced our toolkits by introducing intuitive query and search functions. We also took input from the professionals who's in the medical field for a long time. And additionally, we standardized and seamlessly integrated functions from third-party libraries, augmenting the overall capabilities of our toolkit. MedGen stands as a specialized and all-encompassing NLP toolkit that is only designed for the processing of medical text. This toolkit comprises three integral modules, namely generative functions, basic NLP functions, and the query capabilities. So generative functions will serve as the cornerstone of MedGen. This module encompasses 4 generative tasks, which we will talk in the next slide. So as you can see, this is the model of the MedGen. It has 3 functions: generative, basic NLP functions, and the query and search module. As you can see in basic NLP functions, we have all the 12 modules over there. And we have 4 main sub-modules in the generative functions. Let's talk about generative functions right now. MedGen leverages pre-trained language models, providing users with a suite of capabilities such as question answering, text summarization, text simplification, and machine translation. Users also have the flexibility to tap into any publicly available language models. Furthermore, we offer fine-tuned models tailored for specific generative tasks, all of which are publicly accessible for users to reference and integrate into their workflows. And the next one is question answering. So in healthcare systems, in general, question answering emerges as especially pivotal because its integration into healthcare plays a very important role, including pre-consultation and remote consultation, adeptly managing the surge in patient volume and easing the burden on the healthcare infrastructure. Furthermore, dedicated question answering system process the potential to make significant contributions to patient education and medical training. So we have integrated the question answering function encompassing 2 distinct subtasks, which are multiple choice question answering and answer generation. So what is multiple choice question answering? We equip users with the biomedical multiple questions answering function, enabling them to input both question text and options to ascertain the most likely answer. While primary methodology involves a classification approach, we have innovatively employed generative models in the role of encoders, thus placing these tasks within this category. We also did the comparative analysis extended to 5 pre-trained language models in biomedical clinical domain, namely BioBERT, ClinicalBERT, and SAPBERT, Gaton Trace Base, and PubMedBERT. These models underwent fine-tuning and evaluation using the head QA, which is head question and answer, and MedMCQA find databases. So the databases contains a lot of data and millions of data, and these pre-trained models will tune the data and take the data in and train on that data. And we also took the professionals help with the healthcare system. Additionally, MedMCQA represents a larger data set covering 2,400 healthcare topics and 21 medical subjects. The next answer generation, in addition to multiple question answering tasks, we also offer the capability of answer generation for this particular task. We employed BIS Healthcare and OPT MedAD, both pre-trained on MedQuad dataset, which is comprises of 47,500 odd question answer pairs in medical domain derived from 12 National Institute of Health websites. Evaluations were performed using the QA test collection from the TREC 2017 Live QA medical task containing 2,479 questions and their corresponding references answers. Recognizing the limitation of objective matrices in accurately assessing the quality of generated content, we conducted a manual validation in subsequent sections. 2 healthcare professionals conducted a manual review of 50 random selected answers as well. Next one is text summarization. It's one of the important topic in this one. And the researchers grapple with an exponential influx of information spanning literature, electronic health records, which is also called EHRs, and more. Text summarization emerges as a pivotal generative task, endeavoring to distill vital insights from the intricate fabric of text and represent them in a more condensed format. Automated text summarization proves instrumental for clinicals and researchers, enabling them to efficiently clean essential information while mitigating the challenges of information overload. Within this module, we conducted comparison across general pre-trained summarization models, including Pegasus, Big Bird, BART, and Primera, fine-tuned on general text summarization corpora. We explore domain-specific models such as Sci-Fi and BioBot tailored to biomedical corpora like PubMed and PMC. The PubMed dataset encompasses 133,000 biomedical scientific publications from the PubMed database, with each input document representing a scientific article and reference summarization being the associated abstract. Mimic CXR, on the other hand, utilizes a subset from Mimic CXR from MediQA 2021 radiology report summarization shared task. Due to unavailability of the test set, we repurposed the validation set as a test set and additionally extracted 2,000 instances from the training set to create a new validation set. The next one is text simplification. Biomedical texts are often rife with intricate terminologies, posing a challenge for individual languages and a clinical background, lacking a clinical background. With MedGen, the text simplification functions aims to transform complex and technical biomedical text into more understandable content. The enhancement improved comprehension and engagement for non-clinical individuals, including patients. By rendering the information more accessible, individual can actively participate in clinical decisions with a greater effectiveness. It also involves several pre-trained models, namely BigBot, Pegasus, BART, BioBot, assessed on data sets such as eLife, PLOS, and Medline. eLife and PLOS constitute a shared data task released from Summit 2023, where the objective is to generate less summarization given longer inputs, while the original test set, sorry, to ensure a fair comparison, we conducted a test on a development dataset, reserving some examples from the original training set for validation. Medline, on the other hand, represents a comprehensive human annotated data set featuring professionals to customers, sentences selected from a mimic tree. In the case of Medline, we segregated 2030 examples from the training set to form a validation set. Employing the original test for subsequent evaluation, fine-tuning procedures we applied to select pre-trained models, including Pegasus, BART, and BioBART. The last one is machine translation, and language barriers present formidable challenges for patients, hindering their access to timely information and effective communication with healthcare providers, ultimately resulting in diminished healthcare service quality. By addressing this issue, our machine translation function within the MedGen endeavors to translate text from source language to target language in a clinical scenarios. To enhance the translation capabilities, we fine-tuned existing models such as Marian MT and multilingual T5 using UFL medical corpus. This corpus encompasses diverse medical text sources, including titles, medical Wikipedia articles, medical term pairs, patents, and documents from European Medical Agency. During the processing phase, we excluded general domain from UFL, such as parliamentary proceedings, and meticulously shuffled the medical domain corpora. Subsequently, we split the data into two parts, allocating 85% for the training and 15% for the testing. Each language pair, we harnessed all available parallel data to optimize the breadth and accuracy of our machine translation. The next topic is basic NLP functions. Like I said, we seamlessly incorporated numerous third-party libraries offering comprehensive support for 12 distinctive functions. These functions encompasses abbreviation extraction, sentence tokenization, word tokenization, negation detection, and hypnonym detection, ULMS concept extraction, etc. And furthermore, multiple choice questions too. We can be found for evaluation purposes. We specifically choose to assess the performance of POS tagging and naming and entity recognition tasks. The next one is query and search capabilities. MedGen facilitates user-friendly query and search functions on text corpora through following mechanisms. We included MySQL support for mimic tree database. The data table specifically node events.tsv were meticulously indexed into a MySQL database. We offer user-friendly interfaces and empower users with basic statistical functions, allowing them to retrieve counts of patients, documents, and sentences. Query functionality implements a variety of straightforward query functions like users can retrieve a specified number of patients record or notes by utilizing their respective IDs. Such capabilities will again play an important role of effective search functionality within the unstructured text. We integrated keyword search capabilities. These capabilities, supported by multiple libraries, ensure swift and targeted searches, enhancing the overall user experience. So all the process we done, and we come to the results, and the picture on my right hand indicates the results from the test we did. And for question answering and multiple choice question answering, we leveraged 5 biomedical pre-trained models: BioBert, ClinicalBert, SAPBert, Curtin-Tron base, and PubMedBert. The evaluation metrics employed was accuracy scored as depicted in the picture on the right. The results highlight PubMed but standout performance on head QA and MedMC achieving accuracy rates of 42.52% and 46.59% respectively on MedMCQA, SAP, BERT, Pub, MedBERT, and Gatortron demonstrated comparable performance with Gatortron-based emerging as top performer, boasting an impressive accuracy of close to 65%. Answer generation. The evaluation of answer generation capabilities of two pre-trained models, Bias Healthcare and OPT MedQuad, was conducted using ROC scores. Bias Healthcare outperformed OPT MedQuad across all R1, R2, and RL scores with respect to scores of 21.11 and 5.14 and 19.27. However, it's worth noting that the chosen metrics may not comprehensively assess the quality of healthcare generated content. To address this limitation, manual reviews were performed by two healthcare professionals evaluating content-based readability, relevancy, accuracy, and completeness. The detailed results of these reviews provided in the manual validation section. And the next, text summarization. As you can see, we have different NLP models in the picture and all the respective accuracies of the models. The evaluation of text summarization encompassed both single document and multi-document scenarios with assessment based on ROC scores. We compared the performance of 5 selected models across 4 chosen benchmarks for single document scenario. To ensure a fair comparison, results from BioBot and Sci-Fi, which were fine-tuned on PubMed, were excluded. The observation indicates that BOT consistently exhibits strong performance across 3 benchmarks. Notably, BOT outperforms the Sci-Fi and BioBot in terms of competitiveness. Furthermore, BioBot surpasses BOT on only one of the benchmarks. Additionally, our evaluation extends to multi-document summarization using the MedQA data set as illustrated in the picture. A diverse set of models encompassing both traditional and deep learning approaches were compared. Text rank was employed for extractive summarization, while abstractive summarization considered models such as BART, Pegasus, Primera, and BioBART. And as usual, BART displayed competitive performance with BioBART showing slightly inferior results. The next comparison is among big BART Pegasus, BART, BioBART, fine-tuning, and specifically for text simplification tasks. Moreover, we conducted an analysis of reading ability using Kinside grade level scores. The FKGL score serves as a measure of text complexity, indicating the difficulty of understanding a given text. We compare the outputs generated by our models with ground truth. For eLife and PLO's data set, the ground truth displayed scores of 12 and 15 respectively. Intriguingly, while the BioBot model demonstrated a competitive performance in terms of ROC, it failed as significantly reduced difficulty of understanding as evidence by the scores of 17 in both data sets. All methods appear to reach a similar level of complexity as the ground truth. This could be attributed to a data set shorter examples and potentially smaller vocabulary size, limiting the observed differences. And lastly, machine translation. We fine-tuned Marian MT and MT5 on 3 language pairs, EN, ES, ENFR, ENRO, utilizing Marian MT as a baseline for comparison. Evaluation was performed using BLUE score as depicted in the picture. Following fine-tuning, there is a significant improvement in scores with the most substantial enhancement observed in ENFR language pair. That is English and French. These improvements can be attributed to larger amount of training data available, like 2,81,203 samples. Furthermore, across all three languages based, and the MT5 model consistently outperformed the Mayan MT model in terms of scores. Additionally, we conducted fine tuning for MT5 on five more language pairs, namely ENCS, END, ENHU, ENPL, and ENSV. And from this slide onwards, my teammate Mori will take over.
Yeah, thank you, Rohit. Let me share my screen. Okay. Let me open my presentation. So we have seen all the different use cases or all the different functions the MedGen has in. So now let's discuss about the improvements or the algorithm that we think that it should be implemented or it should be extended in the MedGen. So this is the research paper that got published recently. So it has all the different components, and so we have seen that it is an NLP toolkit that has all-in-one solution for all the text-related processing techniques. So it has generative functions and it has 12 essential NLP functions. So in this, they have tested different functions with different specific domain-based models, and then they have given the results for each of the use case, like what we have discussed till now. Be it question answering, text summarization, text simplification, or machine translation, or different NLP functions, or different other functions that we used in the MedGen, and it has been compared. So coming to improvements, okay, so we will take the use case called text summarization. From there are around 16 functions in this MedGen, so I have chosen text summarization use case. So basically, in the text summarization, all the text, like all the text will be scrutinized to small, where it will be directly pointed to important points or important information. Okay, let me go through the text summarization. Okay, so we know like the data is generated in terabytes or in a petabytes nowadays. Even in healthcare, the health of the patient should be monitored, or all the data will be generated for every second. So, in healthcare, clinicians and researchers are confronted with an exponential surge of information, including literature or data in EHR and more. So, text summarization is an important generative task aiming to distill essential information from the overwhelming complexity of text and compress it into a more concise format. So basically, we use text summarization to make the data in the concise format so that it will be easy for the reader to get the important information from the whole lot of text. So we have used different pre-trained summarization models called Pegasus, Big Bird, BART, Primera, and which are pre-trained and fine-tuned on general text summarization corpora. And we also compare domain-specific models such as Sky5 and BioBart. And furthermore, we choose PubMed, Mimic CXR, and MixQA ANS datasets for evaluation. And this dataset has around 133,000 biomedical scientific publications from PubMed database. Okay, so let's talk about the improvements now. Let me open this one. Okay, so right now, let me show you the MedGen site here. So this is an official MedGen site that has been used by National Library of Medicine, and it's normally you use different fields like different NLP functions like search function, or the database, how the data is getting stored, or how to write queries, or how the okay, let me show you example. If if I say if I am searching for this keyword, it will show all the search results from the database, or it will also show summary of summary of the documents, summary of the text from different fields. I mean, from the different sources. So it will summarize the data from different sources, and it will search using the keyword or using the gene name or using the library ID we give. So yeah, so these are different functionals like how we can summarize the whole lot of data and how we can get the full report page and everything. Okay, so talking about the improvement now. So instead of using all the different 10 functions or all the 12 functions or different functions in the mention, how can why can't we use one single API call so that it will be call in the background and it can be used by any normal user? So they are saying that MedGen can also be used by healthcare professionals who lack domain specific knowledge like the programming knowledge, and they are saying that it is quite useful even for the healthcare people. But I'm sure that even a little bit of programming or computation knowledge is required for healthcare people to operate mention. So I come with an idea like to implement a API integration or creating a chatbot. How we like say we have chat GPT, like that we can create a chatbot for MedGen, like using the Dialogflow CX or using Google Cloud or some other frameworks. You know, we can integrate the MedGen API. We can even uh, integrate OpenAI API. Okay, so we can even create a chatbot platform using Dialogflow or Microsoft Bot Framework or Rasa servers as intermediary between users and integrated APIs. Okay, let me show you how we can integrate these APIs, and I will also come up with an algorithm to discuss to integrate this with our existing application. Before that, I would like you to show the existing code that they got published in the research paper. Let me open this one. So ASCLE.py is the main class for the whole application for the whole NLP toolkit. So it is importing different functions or different libraries, and then it has different arguments like for creating for storing a records or for getting the records, be it single or multi-document task, or using the Skyspace model or BERT model and Marian model for different use cases for translation, for pre-trained transformers, and then for related to Skyspace tasks. So we have a function called update and delete main record and update and keep main record, and these functions, different functions are to keep, update, and get the records. And if we see here the getting abbreviation, this is a function to get abbreviations that inside uses Skyspace model that will get the abbreviation from the text, and then it will abbreviate the text to the patients. Or we also are using Marian model for machine translation, and we have a function called get linked entities. After reading the text, the MedGen toolkit will give us different entities of the text that are connected using the salient score or whatever. And we have named entities function, and we have translation function here. We are getting a sentences and getting tokens, how the sentences are tokenized and how the words are converted to tokens, and then they're transformed to uh, different they can be used for different transformations. And we're also using clustering here to get the supported documents. Suppose if I say I'm uploading 3 documents, and we're If I'm up and then I'm checking for the fourth document, it will give me the cluster of, and it will also give me the supporting records for the given query or given document. And it will also give me the similar documents based on clustering. And we can also get single record or multi-record summary using text summarization. So I took this use case as an improvement, and I will be discussing it more going further. And we also used translation MT5 for getting a for translating everything to a Spanish language. So here we are given target language as Spanish language, and everything will be translated to Spanish. And we also have question answering system that will answer answer the questions, and it will generate a different answers for each the question. And we also have multiple choice here to candidates will have a list which has a default length for, and they can choose one for the different multi-choice, and then based on the choices the patient choose, the MedGen model will give the output for them. And we are using layman text. This is a fine-tuned model for maximum length of 200 for summarizing. So we are using layman text, large LA, fine-tuned pre-trained model for summary use case. And we also have POS tagging, and we also got dialog GPT for getting where to use the GPT services from the function itself. Okay, let me show a small demo here. And this is my project. And so, as I told, ascle.py is the main class, and we're importing ascle. And I'm creating the object called kit, and then kit is an object of ascle class. And then I am so main record will be my main record, and when supporting, I have created two records supporting document one and document two, and I'm using model called Enquiry SCASM, and these are my different arguments. So main record, supporting record, and Skyspace and Marian empty models. So I'm updating the existing records using the functions I have told you earlier. So I'm adding supporting records or adding a main record, and then I'm also replacing the records with the different names. And then coming to abbreviation detection, we have a model called kit.update and delete main record. So I'm then updating this record to my object, and then I'm getting so yeah, I'm using AR SBMA as different abbreviations. So based on this, it will give me the output called SBMA stands for spinal and bulbar muscular atrophy, and AR stands for androgen receptor. And we have different other functionality called hypnopium detection. So it returns a little list of tuples in the form of host pattern, entity one, entity two, and so on, each element being a string. So if I call this function for the above record, if this is a record and I'm calling this function, it will give me the output as such as keystone plan species and with trees. Coming to different other function called getting the different entities. So it returns a dictionary in the form named entity. Named entity consists of list of strings, each describing one piece of linked information. Okay, so this will be by input text, and these are different entities that are linked to each other. And the next one will be named entity recognition. This will be my record, and I'm then updating record, and then I'm getting entities from this record. So here there are different entities, and each entities are uh, divided by a comma. Okay, you can see the output here. And then I'm calling entities here. I'm using stanza tool, and then I'm getting, and then it will show me all the different entities, and also I'm getting different languages that are supported, and this is the output for that. And be it translation, so I'm translating to a French language, so it will be translated to a French language. The given text will be translated to a French language, and this will be the output for the input. Uh, this will be our input, English input, and this will be our French output. Okay. And coming to sentence tokenizer, we are using Stanza, Skyspace, and Stanza Blooms to get different sentences based on these three models. And we have given the results in the documentation. So it's best to go and search on the documentation for the results using these models. And then I am using the get POS tags for each entity that will give a different tags, and it says type of the entity. Like if we say also is an adverb, call is an verb, urance is a noun, it will give an entity a tag for each entity. And let me skip lemmas here, and then let me go to dependencies. So in dependencies, or to get different similar documents, we use get dependency function. It will give all the dependencies based on the salient score or everything. Okay, as I told previously, we are also using clustering for suggesting different documents based on the previous documents. So based on the clustering, we will get similar documents. And this is an example for it. And I just call update a record, and then I just call the function get clusters. So I'm giving the k values to here, and then it is divided into two clusters called cluster 0 and cluster 1 because I have given k is equal to 2. And based on these, the next input will be either going to a cluster 0 or cluster 1. Okay, coming to summarization, this is my kit is my object, and this is my data. So I'm just updating my record, and then I just call get single record summary function. So it just summarized the whole data in a single sentence. Okay, so in this function, we have taken and then we have given maximum value length as 200. So it will then just generate 200 length of data. So it is, and also I have multi-document summarization. It will summarize two records or multiple records at a time. Okay, that's all about text summarization. So we can summarize using single document or using multiple documents. Coming to text summarization improvement. So we were discussing about the integrations, right? Let me show you how we can integrate that. Okay, so the process is there will be a user input. So the user will give an input to the chatbot, and it will analyze the data, and this data will be passed to MedGen API. So MedGen API, like for example, like text summarization or question answering, the data will be taken by MedGen API. MedGen API will be giving you some output from the MedGen backbone function. This output will be passing to OpenAI called GPT 3.4 or some other turbo mission. And this input data is consumed by OpenAI API, and that is fine-tuned on different questions or different summaries, and then it will be prompted as a response to the user. Okay, so that's the improvement we are thinking of, and I will show you how we have implemented BERT and OpenAI API and how we have studied these two models on text summarization use case. Okay, so there are different aspects of making it further. We know that EHR, electronic health records, contains single type of data for each patient, be it publicly available data or privately available data. The data in these systems or in this record should be in the same format so that the data generated by MedGen should be compatible with the EHR. Okay, suppose like if we have data that is generated by our MedGen, it should be compatible with the healthcare databases that are available outside, because this database is used for the analysis by different teams for fine-tuning the models or for further predictions or something, or for the decision making or taking care for the patients. And and there is also possibility of the security concern in this model. So we are using different NLP functions in this toolkit. So the most private data of the user, his healthcare data is passed to these models, and these models are getting predicted for every data generated in a second. So there is a sensitive data passing passing to these models. So there should be some compliances with the data, and it should be taken care, and it should follow HIPAA both guidelines for safeguarding sensitive patient data. Therefore, the integration must prioritize HIPAA compliance to guarantee the confidentiality and integrity of electronic health records. And that's about the future work. So we can talk about how the data can be normalized to a form that can be compatible with the EHR, and how we can take care of the security aspects of training the data or getting predictions from the MedGen model. So coming to the OpenAI code, or integrating the OpenAI GPT for the text summarization use case. And we discussed about the ASCI class and different functionalities in the demo IPY and B file. Let me go to the chatbot file here. I'm importing the request and OpenAI libraries, and then since there is no existing MedGen API available, so this is an I have given space for the API endpoint, and this will be my API key. So I'm using OpenAI ChatGPT 3.5 OpenAI API key, and if this API key will be interacting with the model, and it will give the response for me. And I have a function called get MedGen summary, and the request whatever I'm giving will be passed to this model, and I will get a response based on the prompt. So I have a function called GPT response, and I'm passing a prompt here. Based on the prompt, it will be going to a model. So I'm using text Davinci A003 engine here, and I'm only generating 150 maximum tokens. And this will be stripping the first choice, and then it will be showing me the response here. Let me show you live demonstration here. So the above kit is only for using both MedGen API endpoint and OpenAI endpoint. Let's say if I don't have MedGen API endpoint right now, so how can we integrate OpenAI API with the existing MedGen? So this will be my OpenAI import library, and this is my private OpenAI API key. So when you are running this one, you need to choose your OpenAI, create your own API key, and then you need to replace this one. And this is a function that generate prompt with history. So it will store all the history, and it will take the text as a prompt. Okay, so this a conversation is between the human and AI assistant named Bice. Okay, so every time the history is got appended to the list, and then it will be stored in the history text. Okay, suppose this is my text Davinci 002 engine. I am giving the prompt, and it is taking the prompt, and then based on the prompt is question and the history of prompts will pass to the text. It will store the history as a list, and the prompt and the question prompt, and it will be going to a prompt. And this prompt is used in the function. So these are different attributes for the OpenAI model. So this model takes engine, type of engine, prompt, and the tokens and temperature. So the temperature is known as how effective the summarization could be. So we can adjust the temperature based on our need, and it will just return the first choice, and then it will strip the space from the data. Because this is my data here. So it has, so they're talking about neural network, and they're talking about prescription of aspirin, and they are talking about aspirin prescription, and then and how it can be helpful for relieving headache and reducing swelling and reducing fever and whatnot. Okay, so I'm using the model GPT 3.5 turbo here, and then I just want to summarize the whole data. Suppose, let's say this is the 500 document or 500 length words of data, and going through the patient record as an healthcare professional. I don't have much time for reading each sentence. Let's say this example, and just I want to summarize this data itself. So I don't need to go and call different functions or different models here. I just need to create a chatbot, and I just need to give a prompt. Like how we in ChatGPT we give a prompt. I just create a chatbot, and then I will give a prompt called summarize the text. I have given a content called summarize the text. So it will summarize the text that is present in data. So this is the data that is present inside my data, and this will be summarized. It is as simple as this. So we don't need to call different functions or anything. We know OpenAI or GPT 3.5 has been, trained on multiple labels. It got trained extensively, and it is using multiple GPUs, with multiple GPUs only for training and then testing purposes. So it is an up-to-date AI model that we can trust, and then we can use it, directly, and we can also integrate that with MidGen. Yeah, so that's an easy process as an user who lacks computation knowledge or programming knowledge. I can just give a prompt in English, and then I get data retrieval from the MedGen API or a GPT API. So okay, so this is just a small prompt I have given to summarize the about text, and then okay, this is a use case called question answering. So not only text summarization, we can also use the OpenAI API for different prompts, be it text summarization, question answering, or prompt engineering, or different mission translation and text simplification on different use cases. So here I use for text summarization, and this is question answering. I have given a question: what is meant by myopia and its symptoms? So this is my question here. So it will take the question, and then it will generate the answer for me. Let me run this one. Okay, so this is the first summarization, the OpenAI generated summarization. It says it is discussing, they are discussing, the text discusses two different topics. Yes, that's true. The text is talking about two different aspects. One is about the neural network, another is about the aspirant. So even just looking at this sentence, we can say we can summarize the whole data in this using the OpenAI API, just using a single prompt. And the second one is just question answering, and just asked about what is meant by myopia and its symptoms. So given me a response called it has given me a response called myopia, and then symptoms of myopia of fatigue, difficulty walking, and trouble climbing stairs. This is as simple as that. So coming to conclusion, NLP toolkit is for specifically built for medical text processing, and it has used different NLP functions that has pre-trained, and then compared to native ML model specifically used for medical purposes. And then they compared the results of different models to MedGen, how MedGen is different compared to different naive-based models. And also talked about different functions and different functionalities. And then, okay, here I talked about the chatbot, how we can integrate the chatbot using MedGen API or OpenAI API to existing MedGen function, and how we can improve this using generating compatible data, or talking about or taking care about the security of the data and something like that. And then also researched or BERT compared with GPT models, like how I showed GPT models there. I also checked for the BERT model, and then I given the comparisons based on the different factors, be it performance or training data or latency, or how we can pre-process data in using reduced dependency, or how we can adaptable for different tasks, not only for one specific single task, how we can use it for different tasks, and how we can leverage this for different LLM models and whatnot. And these are our observation that are compared with GPT. And we also checked about Palm 2, but we haven't included in this because we have to do extensive research on Palm 2, and then we'll be coming up with that soon. And that's all about our MedGen research paper. Hope you all like the video. And going back to the Zoom recording, Roy, do you have anything to share?
Nothing more. That'd be all.
Okay. Thanks everyone, and have a nice day.
Yeah, thanks, everyone.
Let me stop the recording now.